Hello, everyone. I'm super excited to share with you our new work on interactive error resilience. The main highlight of this work is that in this work, we show that the value of interactive error resilience is actually higher than what was believed to be optimal for the last few years. Before I explain this result in more detail, let me build up to it by first defining interactive error resilience. I will first start by defining the simpler notion of one-way error resilience. In this setting, there are two parties, Alice and Bob. Alice has an input that is a message M, and she wants to send this message M over to Bob. How will she do this? Well, if the channel connecting Alice and Bob is noiseless, then this task is very simple. She can just send the message M bit by bit. That is, if the message M has n bits, then all Alice needs to do is to send this message across n rounds, where in each round she sends one bit of the message. After these n rounds, Bob has all the n bits, and he can reconstruct the message M. What changes if now we assume that the channel between Alice and Bob is noisy? In particular, we assume that the noise on the channel is determined by parameter theta, which is such that a theta fraction of the messages Alice sends over this channel are adversarially corrupted. So if Alice sends a total of n messages on this channel, like before, then an adversarially chosen theta fraction, or theta n messages, will be corrupted by the channel, but the remaining n minus theta n messages will reach Bob directly. Now, because of these interruptions, Alice cannot simply send the message M bit by bit. However, she still can first encode the message M to a code word C with the property that even after the channel corrupts a theta fraction of the bits in C, it still has enough information to allow Bob to decode and recover the message M. So overall, we reduce the task of sending the message M over a noisy channel to the task of constructing a code with the property that you can still recover the message M from it even after a theta fraction of the bits have been corrupted. Now, one can imagine that the task of constructing such a code becomes harder and harder as the value of theta becomes larger and larger. And a natural question to ask is, what is the largest value of theta for which there exists a code C that will allow Bob to recover M even after a theta fraction of the bits are corrupted? The answer to this question is well known and happens to be 1/2. What that means is that as long as the fraction of errors is less than 1/2, Bob will be able to recover Alice's message. And if the fraction of errors is more than 1/2, then there's nothing Alice can do to send its message across to Bob. As the task of message transmission is one way with only one of the parties, that is Alice, speaking to Bob, this value 1/2 is known as the error resilience of the one-way communication channel. What happens if we move from the one-way to the more general two-way task? One thing that definitely changes is that now, instead of Alice having a message M that she wants to send to Bob, they are both running a protocol Pi and sending messages to each other. Now, the situation is pretty much similar. If the channel between Alice and Bob is noiseless, then they can just run Pi as is by sending each of the messages in Pi one by one. On the other hand, if the channel connecting Alice and Bob is noisy, then say theta noisy, then in order to run the protocol Pi, they first need to encode Pi to another protocol C of Pi, and then run this new protocol C of Pi. This protocol C of Pi has the property that it will simulate Pi correctly, even if a theta fraction of the symbols sent in the protocol are adversarially corrupted. Now, we can ask the same question that we asked in the one-way case. What is the largest theta for which there exists a coding scheme or a simulation, C of Pi, that works even if a theta fraction of the symbols sent in the simulation are adversarially corrupted? However, unlike the one-way counterpart, this new question is open despite being the fortress of 30 years of research effort. Indeed, work on this question started with Schulman's paper in 1993, where it was shown that this interactive error resilience is at least a small constant. 18 years down the line, in 2011, Mark Braverman and Anup Rao showed that actually this constant is at least a quarter. And furthermore, for a class of simulations that are called non-adaptive, 1/4 is the best you can get. In other words, there exists a non-adaptive simulation that has error resilience 1/4, and any non-adaptive simulation cannot have error resilience larger than 1/4. In essence, after the word BR11, all that remains to be done is to know whether or not there are adaptive simulations that can have error resilience larger than 1/4. 3 years down the line, GHS, that is Goffery, Hopler, and Sudhan, showed that yes, this is indeed the case, and they gave an adaptive simulation with error resilience 2/7, strictly larger than 1/4. Now, it was believed prior to this work that this 2/7 value is the optimal error resilience, and no adaptive simulation can have error resilience that is strictly higher. Our main result is that this is not the case. We show an interactive Turing scheme, adaptive of course, with error resilience 7/24, that is strictly higher than 2/7. Thus, this scheme is the first one that surpasses the 2/7 barrier of GHS14, and it also implies that the maximum interactive error resilience lies in the interval 7/24, which is this work, and 8/24, which is the best known upper bound. Cool fact, in a subsequent work, we are able to narrow this down to an exact constant, which lies strictly inside this interval, so we need to improve both the bounds. Anyway, back to this work. You have this scheme that has error resilience 7/24, but this scheme is also great because it's efficient in two other respects. A, it has a constant alphabet, and B, it has a constant rate. Now, the rest of this talk, this was my main result. The rest of this talk will be me describing the ideas that go behind this result one by one and explaining our techniques. For this purpose, I will restrict attention to the message exchange task, which is a particularly simple interactive task. Here, again, you have two parties, Alice and Bob, with input messages MA and MB respectively. And the goal of these parties is to know each other's messages. So at the end of this task, Alice wants to output Bob's message MB, and Bob wants to output Alice's message MA. I emphasize that the restriction to message exchange is only for this presentation, and our result actually gives error resilience higher than 2/7 for all interactive tasks. So why do we restrict to the message exchange task? The main benefit of working with a simple message exchange task, it gives me a concrete instantiation on which I can explain my ideas in this paper. It is also great because it is weakly complete in the sense that if you have a protocol for message exchange with some error resilience, then you get the same error resilience for all other interactive tasks, although you do lose an exponential factor in the communication. So it is weakly complete, but it also captures the 2/7 barrier. And prior to this work, even for this simple message exchange task, we did not know a noise resilient protocol that had error resilience strictly more than 2/7. And therefore, improving it just for this task is the result in itself. Okay, so now let's describe how we improve the error resilience for the message exchange task. But before that, let us first understand how the GHS14 protocol got error resilience 2/7 for the message exchange task. In GHS14, there is the following protocol for message exchange. This protocol has 7 end rounds, which means that the adversary can corrupt 2 over 7 times 7n or less than 2n messages in total. In each of these 7n rounds, one of the parties is speaking and sending their input, and the other party is listening for this input. As the figure shows, in the first 3n rounds, which is stage 1, Alice is speaking and sending MA to Bob while Bob is listening. In stage 2, which is also length 3n, Bob is sending MB to Alice while Alice is listening. Crucial to the correctness of this scheme is the following property. If the lengths of stage 1 and stage 2 are 3n, as depicted, then after stage 2, one of the parties is already sure of its output. So we know that after stage 2, either Alice knows Bob's input MB and can output it, or Bob knows Alice's input MA and can output it. In fact, the length of these two stages is very closely connected to the error resilience 2 over 7. And if you can get these stages to be smaller than 3n while maintaining this invariant, then the error resilience you get will be strictly higher than 2 over 7. Okay? This is the approach we take, and we try to construct a protocol that looks similar, has the same invariant, but in that protocol, the lengths of stage 1 and stage 2 will be strictly less than 3n. During this construction, we are able to exploit the following weakness in GHS14. Observe that in GHS14, when Alice is sending messages to Bob, she's really trying her best. All she has at this point is her input MA, and this is what she sends to Bob. This is not true for Bob, however. In stage 2, when Bob is sending to Alice, he only sends his input MB, but he knows more. He also knows what he heard from Alice in the first stage. In particular, in stage 2, Bob knows whether or not he was sure after the first stage, but he still only sends his input. And the main claim that I will prove to you in the next few slides is that if Bob in stage 2 also tells Alice whether he is sure or not, then we call this information the feedback, then this can lead to an improvement in the error resilience of the protocol. So our new protocol will look like this. It is the same as before. You have the same rounds with the same messages, just that in stage 2, now Bob will send more than just his input MB. He will also send a bit is sure, that is 1, if Bob is sure after stage 1, and is 0 if Bob is not sure after stage 1. And I want to prove to you that with this extra feedback, you can decrease the length 3n of stage 1 and 2 while maintaining the invariant that one of the parties is sure after stage 2. During this proof, I will work under the simplifying assumption. I do not want to work with this bit is sure and tell you how Alice interprets this bit. I will simply ignore it, but assume that after stage 2, Alice magically knows whether or not Bob is sure. So it serves the same purpose, just that I don't have to deal with the bit explicitly. Now let us see why, with smaller lengths for stage 1 and 2, you still know that one of the parties is sure after stage 2, sorry. So 2 cases. We will work with the length that is 8n over 3, strictly smaller than 3n. 2 cases. 1, if Bob is sure after stage 2, then there's nothing to be done. Bob is sure, so one of the parties is sure after stage 2. On the other hand, in the interesting case, when Bob is not sure after stage 2, then due to the presence of feedback, Alice knows this. And she knows that Bob did not receive 2n copies of the correct message. Otherwise, he would have been sure. So Alice sent in stage 1 8n over 3 copies of the correct message. Bob received less than 2n, which means that there were at least 8n over 3 minus 2n or 2n over 3 errors from Alice to Bob in stage 1. As the total number of errors is less than 2n, this means that the number of errors that can possibly happen in stage 2 is less than 2n, the total number, minus 2n over 3, the errors that happen in stage 1, which is equal to less than 4n over 3 errors that can possibly happen in stage 2. This means that in stage 2, Alice receives 8n/3 messages, where less than 4n/3 are corrupted. So in particular, the message that Alice receives most often is correct. Alice can decode to this message and be sure about her output. So we have shown that either Bob is sure after stage 2 or Alice is sure after stage 2, and therefore one of the parties is sure after stage 2. The lengths of stage 1 and 2 are now smaller than 3n. Well, this length is slightly larger, but it doesn't matter. These lengths are smaller than 3n. The number of errors is the same, and therefore the error resilience is strictly more than 2/7. Okay, so this was our mini proof establishing that there is a protocol for the message exchange problem that has error resilience strictly higher than 2/7. In the last section of this talk, I will extend this result from the simple message exchange task to all interactive tasks and get an error resilience larger than 2/7 that works for all interactive tasks. I will build on the same idea of Bob sending feedback to Alice via the is_sure bit that we had, but this new idea will run into several challenges when going for general tasks. For example, the first challenge one would face when trying to simulate a general interactive task is that in general, there is no neat notion of a message that Alice can send or Bob can send to Alice, such that after they have this message, they can finish the task. On the other hand, a general interactive task has a lot of messages in either direction, and these messages are dependent on each other, and they're also all of them necessary to compute the task successfully. Simulating such a task will need similar guarantees from the simulation. The simulation should also have a lot of messages from Alice to Bob, and these messages should be interleaved. And in particular, different from our message exchange protocol where all of Alice's messages are before all of Bob's messages. Okay, so the first challenge is we need to interleave the parties' messages. One simple way to interleave them is to simply have them speak in alternation. Say Alice will speak in all the odd rounds and Bob will speak in all the even rounds. But this doesn't work, and that's our next challenge. It can be shown that if your protocol alternates between Alice and Bob, and Alice speaks in odd rounds and Bob speaks in even rounds, then the maximum error resilience that such a protocol can have is only 2/7. So in order to get an error resilience higher than 2/7, we need to find some sort of a middle ground. We cannot have all of Alice's messages before all the Bob's messages, because then we are not interleaving, challenge 1. And we can't even have adaptation because we cannot even have alternation because we know that any protocol that alternates has error resilience at most 2/7. The solution happens to be the phenomena we call rate adaptation. In our scheme, Alice and Bob still take turns speaking, but when it's their turn to speak, they send a different number of messages to each other. For example, in the beginning of the protocol, Alice will be speaking more than Bob. And in this case, when it's Alice's turn to speak, she will send 4 messages to Bob, let's say, and when it's Bob's turn to speak, he will only send 3 messages to Alice. This will be flipped later in the protocol when Bob is sending feedback to Alice. And here, when it's Bob's turn to speak, he will send 2 messages to Bob, whereas when it's Alice's turn to speak, she will only send 1 message. Okay, we call this phenomena rate adaptation because the parties speak at different rates, and the rates change as the protocol progresses. And it turns out that such rate adaptation is necessary in order to beat the 2/7 error resilience barrier. Okay. The third challenge in a general simulation is something that we skipped over during our message exchange description. We did say that Bob will send an is_sure bit as feedback, which will be 1 if Bob is sure about Alice's message and 0 otherwise. But we did not say how Alice will interpret and react to this feedback. We also did not go over what will happen if the adversary attacks this feedback. And this attack is actually more harmful than all the regular attacks because of the following reasoning. When the adversary interrupts a feedback bit from Bob to Alice, then it harms Alice in two ways. A, it harms the current message, which was obviously corrupted, but B, it will cause Alice to react to a corrupted feedback, which will harm a message later in the protocol. Now, note that this new attack is only possible when the protocol has feedback. So it's an attack that is particular to our current protocol, and is something that a protocol needs to be robust against. Our protocol needs to be cleverly designed so that even when the adversary has this new attack, it cannot disrupt the protocol by that much. Lastly, another thing that we'll need to deal with is that now Alice will need to compute her output differently. Recall that in our protocol, Alice receives two types of messages. A, messages that have the is-sure bit set to true, and B, the messages that have it set to false. And it turns out that she cannot treat these messages equally. In fact, in the new output procedure of Alice, she will assign a weight to each of these messages based on the is-sure bit, and she will output not the majority, but the weighted majority of all these messages. Yeah, this is the last challenge I have in this talk. Once you are able to get around all these challenges, then you get an interactive coding scheme that looks like this. What is awesome is that this interactive coding scheme works for all interactive tasks. It has error resilience strictly higher than 2/7. But I will not give any more details about this scheme and only leave this picture here as my last slide. Thank you.